Okay, so welcome to the calculus series where we discuss about now integration. But before we're able to do that, we must talk about the notion of finding the integral. So consider any curve, maybe something that looks something like this, and we bound it between the 2 points A and 2 points B. How do we find the integral of this? So integral of this. Well, one way we could do it is using a little bit of geometry. What we could do is take little slices every time of the same width but different height. So we could have something like this, where the width is defined by delta x, b minus a divided by n, where n denotes the number of slices. The formal way to say this is the number of partitions. For our height function, our height is determined by this curve, f of x. So our height is denoted by f of x. Recall back in algebra that the area of any curve is some kind of base times height. Well, in this case, our base is just going to be the same as our width. So our area is just going to be some kind of f of x, delta of x. However, this only realistically finds one instance. So we have to add up all these areas. So we can have f of x1, f of x2, delta of x, and before we know it, we have a lot of partitions, or a lot of areas which we add up together. This kind of summation is called a Riemann sum. Essentially, it states that the area underneath any curve is the sum of all the rectangles with a variable height but a fixed width. So we would go from n, starting at n equals 0, which is our, n at 1, which is our first iteration. And this is going to be f of xn delta x, where delta x is, in this case, let me make it consistent. So let's say k instead. K is equal to 1 to n, and we go x of k delta of x, which is defined as b minus a divided by n. N is our number of partitions, b minus a is our boundary points. And we could use this to approximate the area. In the next video, we'll be able to show how we can use this notation to expand into the notion of the integral. Thank you.